Good evening, everybody. Myself Sren Santosh, and I am here to present about YOLO and detecting objects in an image. So, what exactly is object detection? Let's start with an example. We have an image, and when we observe this image, what are all the objects we can identify from it? We see that there is a dog, a cycle, a car, a red scooter, a tree, and a black dustbin. We have observed these many objects just by glancing at the image, and we know exactly where these are present in the image by meaning its location in the image. Now, for a computer or machine to do the same task, it must be able to identify each of the objects properly and classify them, as well as to know their locations as well in the image. So, object detection is basically detecting what the objects are and where they are, and it is one of the fundamental tasks in computer vision. It combines classification and localization. Classification, as I said, what actually the object is. For example, the dog is actually classified as a dog, and it belongs to the class of dogs. And a bicycle is belonging to the class of bicycles, and localization is where their location is on the image. Output we get is bounding boxes plus labels and confidence. Bounding boxes is basically when an object is detected, the area it covers within the image is basically can be considered as the bounding box of that object. And by labels is the classification or classic name given to that object, and confidence is the probability of that particular object exists within that bounding box, and it belongs to that particular class as well. So using non-max suppression, we use it to remove the duplicates that are present in the image. What it actually means is that when we implement the algorithm, there is chances of bounding boxes being uh, duplicated around an object, just to detect the number of what that object is. So when many number of bounding boxes are created, each of them have their own confidence levels. So we only select the confidence levels that has the highest, that is of the highest value, and we do not want other boxes. So we remove other duplicates of them by using non-max suppression. Next, we will see challenges in object detection, occlusion and cluttered scenes. Occlusion and clutter scenes is basically when an object is behind another object. It is not completely visible, and it's just partially visible. So we do not get the proper information of that object. And within cluttered scenes, there is a lot of objects within a small area. So it is difficult to segregate and identify each of the objects. Small and varying object sizes. When we observe an image, there are certain objects which have very small size, and its size and shape cannot be properly understood just by glancing over it. By class imbalance, what it actually means is that when we train the model, are chances of the object being falsely classified as some other class. Say, for example, dog may be classified as a cat or some other object in that image. If so, that is basically what class imbalance is, and this actually happens due to the process of training the model. Real-time efficiency issues. We want the model to be uh, efficient in and work in real time. We cannot have it take a lot of time for computation and produce the results after say 10-20 seconds of object observing an image. That is not ideal, and it's not sufficient as well. So before YOLO, what were the traditional methods used to identify objects? We used HOG plus SVM combination. HOG is histogram of oriented gradients, and it basically describes the shapes and edges of an object in an image. That and Support vector machine is one of the classifiers that learns to separate objects from its background and other objects as well using HOG also. And DPM, deformable part models, it actually uh, models an object by as a collection of parts. So each part is detected separately and computed using features of HOG, and then combined to produce that there exists an object and belongs to this particular class. Then we entered the deep learning era, where we use deep learning algorithms such as CNN, RCN, that is region-based convolutional neural network, and it proposes different regions within the image, and each of these regions, calculations are implemented to detect an object. So these methods are produce high accurate results, but each of them takes a lot of time because it involves multiple stages for just computing the output. That is, it takes multiple segments of that image, detect whether there's an object, and classify it. And overall, the process is very slow. So, what exactly is YOLO? YOLO is short form for you only look once, and this is one of the algorithms, deep learning algorithms, and it was introduced in 2016 by Joseph Redman and his other researchers who worked along with him. And YOLO revolutionized object detection by making this detection as a single step process. The earlier methods used multiple steps to process the image, whereas this YOLO uses only can process the image and give the output within just a single step. So, what exactly YOLO does is it framed that detection as a regression problem rather than classification problem, because the earlier methods used to take different parts, then classify each of them separately, and it was a long process. Whereas this regression, by making it a regression problem, it just predicts the bounding boxes and the class probabilities for each of these bounding boxes from the whole image itself. This makes YOLO very fast, and it's a simple architecture, simple and unified architecture. We have observed in this example that we feed the image on the left hand side to the network, and it resizes the image and runs the convolutional network, and it needs only one convolution network, and it runs it completely, then uses non-max suppression to remove out the duplicate bounding boxes and everything, and it produces the output and gives classifies each of the objects and gives their location as well. So how exactly YOLO works? We see that we give an input image to the system, and it divides that input into S by S grids. So, example, we have 7 by 7, we get 49 grids. Similarly, if we take other different sizes of 13 by 13, 15 by 15, some S by S integer number of grids. And each of these grids will predict B bounding boxes. And each of these bounding boxes has 5 predictions, that is X, Y, W, H, and confidence. X comma Y is basically the center of the image or the center of the object, and W comma H is width and height of the object with respect to the image, and confidence is, as I said, the probability of that object actually existing in that area. And C number of class probabilities. That is, depending on the number of class or objects. Basically, we need to categorize each of the objects to different classes. So, what each of these classes have a probability. So that is the C. That is the class probability C. And so overall, we get tensor, and that tensor is of size S by S into B times 5 plus C. 5 in the sense because we are using 5 predictions: x comma y comma x y w h and confidence, and it combines the overall output to produce class probability into confidence into IOU for final detection. That is, in the final detection, this is the output we produce, and IOU is the intersection over union between the predicted box and the ground truth. Basically, what it means is that in the bounding box, it actually intersects the area. It actually measures how much the predicted bounding box overlaps with the actual box. That is, an object basically exists in that area. So, as I said, the input image is divided into S by S grid, as in the image, and we take different number of bounding boxes. As I said, each of the object may have multiple bounding boxes, and from these bounding boxes we produce we get 5 predictions: x, y, w, h, and confidence, and each of the class probabilities. Then we use this class probability map and that bounding box and the confidence to take our final detection. That is the product of class probability, confidence, and the intersection over union. Next, let's discuss about the architecture of YOLO. YOLO actually is a neural network that has 24 convolutional layers and 2 fully connected layers. And it is pre-trained on ImageNet dataset and fine-tuned for detection purpose. And this neural network uses leaky ReLU, that is leaky rectified linear unit function as the activation function for the neural network, and uses dropout regularization. And it uses custom laws for localization, confidence, and class. That is, certain losses occurs when we take to avoid this. We use custom laws for localization. This is the architecture. As I said, we have a total of 24 convolutional layers and 2 connected layers at the end, and each of these layers have are as shown in this image. Now let's discuss about the strengths of YOLO. YOLO is basically a unified system, and it is unified architecture. It consists of everything like classifying, detecting, and predicting actually, and it gives all in a single step as well. And it is end-to-end trainable. That is, you just feed an image and you get output within that single step itself, and you get it proper as well, and is extremely fast when compared to other previous models, and it's very useful for real-time detection. And how this works is YOLO actually uses the entire image, so it provides the global context rather than use how we see in RCN, where it takes different parts of the images. So it gives very localized context as well. And it's YOLO learns generalizable object representations. That is how general the object appears, and it performs well across other domains as well. Like, it's not particularly only observed for real-time images or some other. It is very useful in detecting different arts in photos to understand different faces as well. So limitations of YOLO. Localization error is occurs due to the grid resolution. Depending on the resolution of the grids we use while dividing the input image into grids, tend to get a lot of localization error, and it struggles with very small or overlapping objects. As said, occlusion and clustered objects in an image will produce difficulty in detecting and classifying an object. And each grid cell can only detect a limited number of objects. And equal error weightage is used for large and small boxes within the image. So the different versions of YOLO. First, we got YOLO version 1, then we got YOLO version 2, and it introduces Darknet 19 backbone architecture, and it added uh, Darknet 19 backbone is actually the better feature extraction, and it uses batch normalization and it allows faster training and better convergence by using anchor boxes and multi-scale training and pass-through layers as well, and because it is useful for different resolutions, and it becomes more robust for to different resolutions, and it, it can train jointly on detection and classification for over and recognized over 9,000 plus classes by hierarchical learning. YOLO version 3 uses DarkNet 53 with residual blocks, and it also uses multi-scale predictions like 13 by 13 size, 26 by 26, 52 by 52, small, medium, and large. And it uses binary class predictions for multiple label support, and it has better small object detection from compared to version 1 and 2. And version 4 uses CSP Darknet 53 backbone, PANNet, specify pyramid pooling neck. And it also, there's a scaled version of version 4, which has scalable width, depth, and resolution. And it is mainly optimized for hardware purpose, for different hardwares. And YOLO is still developing and it's still evolving, and each of when we observe these with the previous versions, we observe the trend that it is getting faster, smarter, scalable as well, and it increases in accuracy and efficiency. Applications of YOLO. So where exactly YOLO is used? We have a numerous number of applications for YOLO. Autonomous driving. Now, with the onset of self-driving cars and a lot of detection systems, we see that YOLO is a necessary application in all of these. In the sense, we have to detect pedestrians, traffic signals, vehicles, and other objects on the road. That is, the vehicle has to detect them and make split decisions to avoid them, to brake at the right time so as to not cause harm to the driver as well as other pedestrians and vehicles. Healthcare imaging. YOLO is used to detect used in medical field to detect tumors and other health problems as well. In agriculture and drones, in agriculture, we can use it to detect weeds from a spatial image, or as a drone keeps moving over the farm. It can be used to detect fruits, weeds, insects, animals grazing, and etc. And so the farmer can understand how his field is and take the necessary steps to get it better. And in surveillance and robotics, CCTV as well as traffic systems use YOLO to detect uh, vehicles, their numbers, as well as robots use YOLO in their visual systems to identify objects when something crosses its path, or to identify a human and to respond accordingly. Impact and legacy. So, as I said, YOLO is a unified framework for detection. It is the complete package, and it inspired the SSD, that is the single shot multi box detection. It uses features maps from multiple CNN layers to detect objects at different levels, scales as well, and detection transformers, that is used transformers for detection instead of CNN based region proposals and efficient data. And it is open source, and as well as it is growing and adopting as well. Future trend is it is used. We can observe. We can hope for it to be available in our edge systems, such as mobile phones and smaller models, so that and to make it lightweight deployment, we can use it at mobile phones itself to detect objects and classify them. Transformer based YOLO models are also existing right now, and version 8 and more usually consists of transformer based models and multitask detection and segmenting of objects, and in using aware of in ethical practice of AI and privacy. So, in conclusion, YOLO actually transformed what we had in the object detection with speed and simplicity, and it has made the problem much simpler. And now it is evolving, and it will keep evolving for it has been evolving for over a decade, and it will keep evolving. And the philosophy of this YOLO is, as I said, the name already suggests, you only look once. And just by looking at an image or a scene once, we have to gather the most efficient and most number of data from just by glancing at it. Thank you.